Tell me, what were you looking for? Ability to make a hydrogen bond. Cool. All right, so tell me, what'd you get? Pardon? Glutamine. Glutamine. Yes, that would absolutely work. Excellent. All right, thank you, sir. So, glutamine. And just to be, it has its NH2 at the end, and it could make a hydrogen bond to the lone pair on the oxygen there. All right, cool. How about another one that could do that? Another alternative, yeah. Aspartic acid. All right, so that's actually a really good one. Aspartic acid can't make a hydrogen bond there because, but that's actually, aspartic acid can make hydrogen bonds, but not with that partner. Let me show you what I mean, because I'm actually really glad you said it. I was hoping somebody would say it. So aspartic acid, at its end, it's got CO with its bunch of lone pairs and an O minus, right? And you're trying to make a hydrogen bond with this. What you've got is this is an H bond acceptor, and this is an acceptor. So what it means is you cannot form okay? You can't, so although aspartic acid can make H bonds under some circumstances, and although that little piece of the backbone can, you've got acceptor with acceptor, and so they cannot form a hydrogen bond. So everybody click, that's important. Levi, what are you going to say? So let me be careful. This problem is a little bit tricky. Valene side chain, no way hydrogen bonds, right? It's all just carbon and hydrogen, boring itself, hydrophobic. But it happens we're making a hydrogen bond to part of its backbone. It's kind of a weird exception to what we normally talk about. So we're making a hydrogen bond to part of the backbone. And that part of the backbone is that oxygen up there. All right. So this is a little bit weird, but if you follow it along, I mean, you'd never make a hydrogen bond to the side chain of valene. Forget about it. But the backbone has a little possibility there. All right. Other questions? Yeah. So there were two things you said. Let me take the second one first. You said, I thought we were only doing side chains. You can make a hydrogen bond to the backbone. This is the one time we'll do it. In everything else that we talk about, it's always going to be side chain stuff. We won't. This is one exception because it turns out there aren't that many hydrogen bonds in hemoglobin that you can find. So this is the best one I could find, which is a little weird. The second question, the first thing you said was glycine is another possibility. Pardon? Pardon? Oh, lysine. Lysine, yes. Lysine will do it too. Let me write that. That's another one. Let's we should make a list. You can also do lysine. How about another possibility? Histidine will do it. Serine will do it also. Another one? Pardon? Oh, you got to raise your hand. Sorry, everybody said, yes. Tryptophan. I'm going to put a star on that. Hang on one sec. So tryptophan, it's got an NH. I've heard people say that because it's on that complicated ring thing, it can't make a hydrogen bond in real life. We will say that it can in Bio 111. It turns out to be slightly more complicated. Let me get one more. Exactly. So what she was saying is exactly, since we have an acceptor, a partner for that is a special hydrogen. It's a donor. So and there are many more. All right. Yeah. No, not backbone to backbone. In this case, it's side chain to that thing. Yeah, in this particular case. All right, let me do one last kind of bond. And that's this. Here, deep in the middle, you got a bunch of amino acids, and they're doing a hydrophobic interaction. All right? Snuggle up in the middle of the protein. One of the things I want to show you about this, because I want to ask you guys some examples in a second, is, well, you tell me, a protein, if I take beta globin and I slice it like on a deli slicer and open it up, what's the inside going to be mostly? Phobic, philic, or a mixture? Mostly phobic, because that's where they're going to snuggle up with their phobic buddies and stay away from the surface. So you can do that, it turns out, figuratively speaking. So red is hydrophobic, white is hydrophilic. And if you let this, it does its thing. We've just now taken a slice. We've just chopped off a slice of beta globin, and we're looking inside. And you see that the inside is mostly, but not entirely, red. And if you take further slices as you slice along it, you can see that here we are at the outside. And as we're taking a slab of bologna and slicing it down, what you can see is the inside tends to be more hydrophobic, more red than the outside, which is what you would expect. That's what glues these things together into the shape that they have. So let's do one last example, and that's this phobic effect. All right, between Lu 68 and Phi 71. So an amino acid that could substitute for, say, Lu 68 here. So think about it a minute, talk to your neighbor, call on somebody.